The speed of light in a vacuum, approximately 299,792 kilometers per second, defines the absolute limit of data transmission. Fiber optic cables, the current backbone of global connectivity, inherently slow this speed down by roughly 45% due to the silica glass refractive index, typically 1.45. This physical constraint means a terrestrial fiber link spanning 5,000 kilometers requires a minimum of 24 milliseconds for one-way travel. Starlink, operating in low Earth orbit, exploits the vacuum of space for its primary transmission path. This fundamental physics difference allows LEO constellations to achieve significantly lower latency on transcontinental routes, despite the longer geometric path length, because the signal travels at the maximum possible speed for the majority of the journey. This is the core technical reason why LEO is not just an access technology, but a potential competitor for high-speed backbone traffic. Terrestrial fiber latency is calculated using the effective speed of light in glass, which is closer to 207,000 kilometers per second. Furthermore, fiber routes rarely follow a straight geodesic path. They must navigate terrain, infrastructure, and regulatory boundaries, adding significant physical distance. Long-haul fiber links also require periodic signal regeneration and amplification, introducing measurable processing delays at repeater stations. While these delays are minimal per station, accumulated over thousands of kilometers, they compound the inherent speed reduction. For example, the shortest physical fiber route between New York and London is approximately 5,800 kilometers, resulting in a theoretical minimum latency of around 28 milliseconds, excluding all switching and processing overhead. This nonlinear routing penalty further degrades fiber performance relative to the straight-line potential of space-based links. Starlink satellites orbit at approximately 550 kilometers. A signal traveling between two distant ground stations must ascend and descend through the atmosphere, but the vast majority of the path is vacuum. Consider a 5,000-kilometer separation. The signal travels up 550 kilometers, across the constellation via multiple satellites, and down 550 kilometers. Although the geometric path length in space is often longer than the straight-line distance on Earth, the 45% speed advantage in vacuum propagation overcomes this distance penalty for long-haul routes exceeding roughly 3,000 kilometers. This makes LEO constellations particularly attractive for latency-sensitive applications connecting geographically disparate financial markets. The key is minimizing the time spent in the atmosphere and maximizing the time spent in the vacuum of space. The latency advantage of LEO is partially offset by necessary ground segment processing. The user terminal must acquire, track, and maintain connection with rapidly moving satellites, requiring complex beamforming and Doppler shift correction, which introduces processing delay. Furthermore, the signal must traverse the troposphere and ionosphere, adding minor atmospheric delay. Crucially, the constant handoff between satellites as they move across the sky requires rapid switching and routing decisions, adding several milliseconds of overhead compared to a static fiber connection. Minimizing this ground segment latency is a continuous engineering challenge and a key differentiator in LEO system performance. This overhead is a fixed cost that must be subtracted from the theoretical vacuum speed gain.
Inter-satellite links, or ISLs, are essential for achieving true transcontinental low latency. These are high-speed laser communication links that allow satellites to route data directly between themselves without needing to descend to a ground station midway. Without ISLs, a signal must travel up to a satellite, down to a ground station, across terrestrial fiber, and then back up to another satellite, negating the vacuum speed advantage. Laser ISLs operate at the speed of light in vacuum, creating a space-based mesh network that bypasses terrestrial infrastructure entirely. This capability transforms Starlink from a simple access provider into a global, low-latency backbone operator, competing directly with submarine cables and dedicated fiber networks. The deployment of ISLs is the single most important technological step enabling LEO to challenge long-haul fiber. In high-frequency trading, every microsecond translates directly into competitive advantage and profit potential. LEO systems targeting routes like Chicago to Tokyo or London to Singapore offer a measurable latency reduction over existing fiber, justifying premium pricing for financial institutions. Beyond finance, enterprises utilize LEO for resilient, low-latency virtual private networks, particularly for disaster recovery or connecting remote operational sites like mining or energy platforms. The ability to deploy a high-speed, low-latency link independent of local terrestrial infrastructure provides significant operational flexibility and redundancy, driving adoption in sectors where connectivity failure is catastrophic. The business model for LEO backbone services is fundamentally predicated on selling time savings. Unlike dedicated fiber, LEO constellations are shared resources, meaning capacity and latency are subject to network congestion. Starlink employs dynamic routing algorithms to manage traffic load across its satellite mesh, prioritizing latency-sensitive traffic where possible. The business model relies on maximizing throughput per satellite while maintaining service quality. As the user base grows, managing cell capacity becomes critical. Starlink must continuously launch new generations of satellites with increased throughput and improved ISL capacity to prevent latency degradation, which would erode its competitive advantage against fiber in densely populated areas. Capacity management is the primary operational challenge that differentiates LEO from fixed terrestrial infrastructure. Operating a global LEO network involves navigating complex international regulatory frameworks, primarily governed by the International Telecommunication Union. Securing spectrum licenses in the Ku, Ka, and V bands across dozens of sovereign nations is a massive legal and logistical undertaking. Furthermore, the increasing density of LEO satellites raises concerns regarding orbital debris and collision risk, necessitating compliance with emerging space sustainability guidelines. These regulatory and environmental compliance costs represent significant long-term business risks and operational expenditures that terrestrial fiber networks largely avoid. Regulatory approval dictates market access and operational footprint, directly impacting revenue potential. Future LEO generations are exploring higher frequency V-band spectrum to increase capacity, although this introduces greater susceptibility to atmospheric attenuation, known as rain fade. The long-term business strategy involves integrating LEO connectivity directly into terrestrial 5G and future 6G networks, creating hybrid systems. This integration allows mobile operators to offload traffic and extend coverage seamlessly into areas where fiber deployment is cost-prohibitive. Ultimately, the market will likely settle on a complementary model, fiber dominating short-haul, high-density metropolitan areas, while LEO dominates transcontinental backbone traffic and remote access, optimizing for latency where the vacuum speed advantage is maximized. This convergence defines the next phase of global telecommunications infrastructure.